Hello everyone, welcome back. In today's video, we're going to be covering the fundamentals of CMOS circuits and CMOS logic. If you ever wondered how a chip actually decides whether or not it's going to output a logic 1 or logic 0 at the transistor level, we will be covering that in depth in today's video. We'll start with the transistor equations themselves, build up to the basic logic gates, and by the end you'll understand not just what a NAND or XOR gate does, but why it is built the way it is. So everything in CMOS logic and CMOS circuits comes down to two transistor types working together. You have the NMOS and the PMOS. On the left-hand side of the screen, you'll see the NMOS, its schematic symbol, along with its three key equations for the three operating regions. That would be the cutoff, linear, and saturation regions. On the right-hand side, you'll see the PMOS circuit schematic along with the equations for the similar cutoff, linear, and saturation regions. Now, if you'll notice, the equations are exact mirrors of each other. The NMOS and PMOS are the exact same, just with the signs flipped. So if we look at the NMOS equations, you'll see cutoff is when your VGS is less than your VTH, that being your voltage between the gate and the source terminals is less than the threshold voltage that is inherent to the MOSFET you're using. The linear region is when your VGS is greater than your V threshold, and this is where current flows through the device, and that is the same behavior exhibited in saturation. However, you'll start to see some current pinch off in the saturation region, whereas the linear region almost acts as a resistor. So at a high level, the NMOS allows current flow between the drain and the source terminals when VGS is greater than that V threshold, and PMOS allows for current to flow when that VGS is less than that V threshold. Now, again, PMOS is a exact mirror image of the NMOS when looking at those equations, and I claim it's important to understand why that is, not just acknowledge that that is a fact. So here's the why. PMOS conducts using holes instead of electrons as the majority carrier, and that's what makes its threshold voltage negative rather than being positive. So VTH, or your threshold voltage, being negative for PMOS is the direct cause of every inequality having those signs flipped. And it's the exact same transistor physics as the NMOS, it's just referenced from a negative threshold instead of a positive one. So that symmetry isn't just a neat coincidence or anything like that. It's the entire reason CMOS logic works the way it does. So keep this mirrored relationship in mind because it comes up again and again as we build actual gates. Alright, so the simplest possible CMOS circuit that you can come up with and the most fundamental to digital design is the inverter. So as you can see on the left-hand side of the screen, we have the input-output truth table along with the schematic associated with the inverter. And on the right-hand side, we have the truth table associated with a buffer. And a buffer is just going to be two cascaded CMOS inverters. So let's take a bit of a deeper dive here and analyze each circuit behavior using the truth table. So if we take a look at the first test case, we'll have an input of 0 and an output of 0. So if we feed a logic 0 or a ground to the input of this CMOS inverter, we will effectively allow for current to flow through the PMOS in the pull-up network that's between VDD and our output, and we will not allow current flow between the NMOS that's in the pull-down network. So a input of 0 will effectively tie our output to VDD, giving us an output of logic 1. And again, a 0 at the gate of the NMOS will not allow for current to flow through the device. Now, if we look at the second test case where we input a 1, the inverse is true. So current will not flow in the PMOS, and current will flow through the NMOS, effectively tying our output to ground or 0 volts or logic 0. And as I mentioned, a buffer is effectively just a cascaded or two cascaded inverters. So if we make that connection here, tying the output of the first stage to the input at the second stage, we can now follow the same methodology here and analyze the circuit. So if we have a input of 0 at the second stage, the PMOS will allow for current to flow through and tie our output to 1, or VDD, and the inverse can also be done. So if we have a 1 at the second stage, the NMOS will allow current to flow through, effectively tying our output to 0 volts or logic 0, and this effectively acts as a pass-through from input to output. Now we're going to take a look at the CMOS NAND gate, and as you can see, we've started to combine transistors into networks instead of single pairs here, so things are getting a little bit more complicated. And this is a 2-input NAND, and the number of transistors will obviously scale as you go to 3, 4, or even higher input NAND gates. So yeah, let's use the truth table in tandem with the schematic. So if we look at the first input scenario where both inputs are 0, current will flow through the 2 parallel PMOS transistors in the pull-up network and will not flow in the 2 series NMOS transistors in the pull-down network, effectively tying our output to 1, or VDD. The second test case will be 0, 1, which should output 1. So if we follow the same methodology, that bottom NMOS transistor will allow current to flow, but the second one will not, so our output gets connected to, once again, VDD through the parallel combination of those 2 PMOS transistors in the pull-up network. And a similar logic unfolds for the 1, 0 test case, where only one of those series NMOS transistors allows for current to flow, and one of the PMOS transistors that is in parallel allows for current to flow, effectively pulling our output to logic 1, or VDD. And for the all 1 test case, neither of those PMOS transistors conduct, and the 2 series NMOS transistors in the pull-down network conduct, tying our output to 0 volts, ground, or logic 0, depending on what you want to call it. Now, I did make this circuit in LTSpice and ran a simple simulation, and you can see that exemplified here. So if we go back to our NAND truth table, you'll see that the output should always be 1 unless all of our inputs are 1 for a 2-input NAND. As you can see, our LTSpice circuit exhibits exactly that behavior, where only for this predefined period is our output 0. Everywhere else, our output is logic 1. Okay, now let's repeat the process for the CMOS NOR gate. So if you'll notice, the NOR is the structural opposite of NAND. The pull-down network is 2 NMOS transistors in parallel, and the pull-up is 2 PMOS in series. More on that in a coming slide. So let's repeat the same analysis with a 0, 0 input, which will allow for those 2 series PMOS transistors to allow current to flow through, tying our output to VDD, or logic 1. For a 0, 1 input, only one of those PMOS transistors will conduct, whereas one of the NMOS in the pull-down network will conduct, tying our output to 0 volts. And the exact same behavior can be exhibited for the 1, 0 test case. Just the other NMOS transistor will tie the output to 0 volts or ground, giving us an output of 0. And lastly, if all of our inputs are 1, both those NMOS transistors will conduct, tying our output to, again, 0 volts or ground. So again, I made this circuit in LTSpice and did a simple circuit simulation. So if we go back to our truth table, you'll see the output is 1 only if both inputs are 0. And if we look at these waveforms here, they exhibit exactly that. Our output is only 1 when both input A and B are 0. And you'll notice as soon as this input goes high, our output goes low. And you can see that repeated here once more, and lastly at the right side of the screenshot. So this duality design rule that I've kind of alluded to in previous slides is really important. So it's the generalizing idea behind everything that we just built and analyzed. And the key pattern here is that NAND use series NMOS and parallel PMOS, and NOR use parallel NMOS and series PMOS. Every time the pull down and pull up networks are the exact structural opposites. Series in one is parallel in the other. And that's essentially it. That's the duality design rule. You can effectively build your own pull down network to match the on condition of the function using NMOS, where series effectively acts as and parallel acts like OR, and the pull-up network is always the complete opposite of that structure, or complement in another way. It's also worth pausing on why the pull-down network is always NMOS and the pull-up is always PMOS, never the other way around. NMOS is excellent at pulling a node down to a solid 0 volts, but it's bad at pulling up. As the source voltage rises, VGS shrinks, and once it drops below the threshold, the device just shuts itself off, stalling out short of a full VDD. PMOS has the mirror image problem. It's great at pulling up to a strong VDD, weak at pulling all the way down to true ground. So the assignment is anything but arbitrary. NMOS only gets asked to do what it's good at, pull down, and PMOS only gets asked to pull up. That's what guarantees a full logic swing between 0 and whatever your logic level is. Let's say, for the sake of this example, 3.3 volts. If you tried flip-flopping that, you would see a lot of weird behavior that would not cleanly represent the logic functionalities. Here's a natural question that'll sort of build off of what we've already seen. You've seen NAND. Now let's look at AND, which, if you'll notice, it's just a NAND gate with a cascaded inverter on the end. So we'll follow a similar analysis. Look at the all 0 input test case. You'll see that those two PMOS will allow current to flow, tying the input to that inverter to VDD or logic 1, which will turn on that pull down NMOS, tying our output to 0. Input 0, 1. One of those parallel PMOS in the pull-up network will allow current to flow. VDD will be sent to the inverter in a similar fashion and tie our output to 0. The exact same logic tracks for input 1, 0. It will lead to an output of 0 again. And lastly, if we look at the all 1 test case, those bottom two series NMOS transistors will allow current to flow, passing on a ground or 0 volts to the inverter, which will turn on that PMOS, tying our output to VDD, giving us an output of logic 1. All right, now let's take a look at the CMOS OR gate. Again, is just a NOR gate with a cascaded inverter. Let's look at the all 0 input test case. Those two PMOS will allow current to flow and pass a VDD or logic 1 to the inverter, energizing that NMOS and tying our output to 0. For 0, 1 and 1, 0, only one of those PMOS in the pull up network will allow current to flow. One of the NMOS will feed a 0 volts to the inverter, which will energize that PMOS and tie our output to VDD or logic 1. And lastly, for the all 1s test case, those two NMOS in the pull down network will feed a 0 volt signal to the inverter. Again, the same behavior. The PMOS will allow a connection between our output and VDD, giving us a logic 1 output. Lastly, we'll be looking at some more complex CMOS logic gates, that being the XOR and the XNOR. On the left-hand side of the screen, you'll see the XOR truth table. And on the right-hand side, you will see the XNOR truth table. They're just inverse of each other. The logic behind a XOR gate, at least with a 2 input, is the output is only 1 if the inputs are not equal. So as you can see, the output is 1 for 0, 1 and 1, 0. So on the left, you've got the XOR gate, and on the right, you've got the XNOR gate. Now, I tried to make it a little simpler to follow by just using the B bar, A bar inputs to indicate the inverter sitting on the front of those gates. So if we test out the all 0 input, the two pull down NMOS transistors will conduct, tying our output to ground, giving us a logic 0 output. And if both inputs are 1, the other two diagonal transistors will conduct, tying our output to 0 volts. Now, if we take a look at the other cases, like 1, 0, for example, this is where it gets a little confusing with the A and B bar. You will see that for 0, 1 and 1, 0, one of those two parallel combinations of A, B bar, or A bar, B will conduct, tying our output to VDD or logic 1. And now we can turn our attention to the XNOR gate, which, as you can see, the principle of duality is at play here, where we've effectively just mirrored everything. And now you could tie as I was drawing there, you could tie a inverter to the output of a XOR gate, but in the interest of minimizing the amount of transistors, you could design an XNOR in a fashion like I've done on the right-hand side of the screen. So this XNOR gate has a very similar behavior. So if both the inputs are the same, so 0, 0 or 1, 1, the output will be tied to VDD or logic 1. And if the two inputs are not equal, the diagonal NMOS pull-down network will pull it to 0 volts. Thank you.